Hello, I'm Esmail Khorasani Javadi, and today I want to talk about crystallography. But before start the main topic, I want to give you an introduction about crystallography. And when we are talking about crystallography, it's obvious that we are talking about crystals, and it's obvious that crystals are made of solid things, and solids are so in touch with us, and we are familiar with them. But what is crystallography? As I told you, when we are talking about crystallography, we are in touch with crystals and the field that study crystals, their behavior, their properties, and whatever you can think about crystals. It's crystallography, and it's important. If we know the crystal structure of a material, crystal, I'm sorry, crystal structure of a material, we can know many properties of that material. And by knowing that properties of material such as its mechanical properties, uh, we can guess many behaviors of that material or the substance that we have. And as I mentioned, the solids, what are the solids and how many shapes they have, or better to say, how many types they have, I'm gonna uh, tell you in the next slide. Solid types. Consider us as solids. We can at least have two types for solids. Um, Crystals, that is the main topic in this lesson, and amorphous solids. That the amorphous solids itself has two types. One of them has no uh, orders, and one of them has short range order. If I want to tell you what a crystal is, I can uh, say crystals. In two-dimensional, you can imagine this square and this triangle, and look at this square. This is repetitive in whole the material, and this triangle is also repeated in whole material, and it has a long range order. What does it mean? It means that whole of the material we have obey this cell, or about this one too. All the material is obey this cell, and of course there is no gap between these two cells. And these materials are so important to us because if we know uh, what properties this cell has, we can talk about the whole this whole structure, we have all the material, and it's more easier for us uh, uh, to study one cell, and then uh, we can match that with all the material we have. So, and they are so important to us. But what about amorphous solids? Amorphous. Uh, Consider this as a solid structure in two dimension. I'm sorry, and you cannot find any order in this material substance, but it is the no order solid. But if we have a structure like this as a solid, for example, you can find some orders in some part of the material, but not in the whole material we have. I'm sorry. Look at this. These are repetitive in our material, but not in a long range order. It's short range order. We have a short range order for this material, and we call these materials that they have no shape. They have no shape, amorphous solids. And if I want to give you example of these amorphous solids, I can talk about this iodo. It has two shapes. Actually, most of the materials, or we can say all of the materials, have two shapes: crystals, crystallic, and amorphous. Crystalline and amorphous. Crystalline, amorphous. We're gonna talk about this later, but what about the amorphous one? Um, Look at this. Consider this as a glass. As you know, most of the glass structure is iodo, and this is the start point. The first time that we made this glass, and we have installed that on our window, and it's stand like this, and after 50 years, what will happen to this glass? I will tell you right now. Consider this dimension as x, also here as x, but after 50 years we're gonna find it shape like this bit below. Actually, this not gonna be this much I don't know, difference between this and this after 50 years, but uh, uh, for for explaining that it's a good picture or good shape. After 50 years, we're gonna have here as x minus x prime, and here x plus x prime, or better to say x second. Uh, what will happen? Why this happened to our glass? Because our bonds, our atoms, our material are getting down. They are moving downward. They are like liquid. travel up to down, and you know, mm, their bonds aren't gonna move downward because our amorphous solids are uh, liquids with a very high viscosity. That much high that we cannot consider these amorphous solids as liquids, but our bonds, our substance, our material or atoms, we move and can uh, they can move actually. They have enough energy to move in our substance or in our material. But we're talking about atoms, about our materials, about our solids. What are atoms? Well, consider this material as a solid. But let me change the shape. Consider this as a material, as a solid. How can we understand this is solid? Consider these circles as atoms of solid. Uh, these atoms have some exact energy. They cannot move easily. They cannot leave this body. They cannot leave this. Uh, um, they cannot leave this tube because they don't have enough energy to leave this structure. Why? Because in our solids they cannot leave. They cannot um, lose their place, or better to say, they cannot uh, leave their place. They can just vibrate where they are. Okay, but what are atoms? Consider this as the nucleus of an atom and its orbitals that our electrons are circling around the nucleus. This is the nuclei, and these are the orbitals. And nuclei is made up of protons, neutrons, and we have electrons here. And electrons are orbiting around the nuclei in these orbitals, and electrons have one negative charge and protons have one positive charge and neutrons are neutral. And consider this atom uh, as, for example, consider this atom has two protons and two neutrons. That I show the neutrons with blue and protons with purple. If we take a photo of this nuclei at the first place, and in the second step we again take another photo, these protons and these neutrons are also moving inside the nuclei in the this radius. That nuclei is stable. uh, we can, if we have this as 1 and this is 2, this gonna be, for example, 2, this will be 1, and if this is 1 and this is 2, this one is going to be, for example, 2 and this is going to be 1. Why? Because our uh, mm, nuclear particles, that are protons and neutrons, are moving inside the nuclei, and we call these as the nucleons of the nuclei, and uh, electrons are electrons. And let me bring you a photo of an atom and have more explanations. So consider this as an atom. For example, this atom has the blue ones as neutrons and red one as protons, and these are the electrons that are orbiting around the nuclei. And let me bring you a better shape. For example, this one. You can see that protons have positive charge and neutrons are neutral, and electrons have one negative charge. And it's obvious that for an atom, Ne, that is the electron numbers, and Np, that are the proton numbers, should be equal because of the neutrality of the atom. And this is a good picture that I can explain this more. Consider this nuclei like this. This is the protons, and these are the neutrons. Okay, but I don't want to talk about the nuclei of this atom. Look at this. This is a cloud of electrons around the nuclei. And when we get far from the nuclei, by having more radius and adding to the radius, you can see that this cloud is be more, colorless, or better to say, it's so transparent. And this is because that when we get near to the nuclei, the effect that nuclei can have on these electrons is much more than here or here or here. And when we get too far from the nuclei, for example here, electrons are leaving the atom, and our atom will lose its electrons because the nuclei cannot take its electrons more than far than this radius, because the effect is gonna be less and less and less by adding to the radius of this cloud. But another thing that I want to say that is the if you consider I'm sorry, it is if you consider this as energy levels, this is the energy level, and if we have this level as 2 and this level as 1, the materials that are more stable, they like to be here, not here, because this is the lower energy than this. When we add to the energy, they want to lose their energy and free themselves from that energy. So when we have less energy, when we decrease our energy, we have a stable level, and because of this, when we get nearby the nuclei, electrons are more stable than here or here and here. They like to spend their time near the nuclei, then they circle around the nuclei near of that nuclei. And Let me bring you a shape of crystal material and a non-crystal material. Look at this. This is a crystalline solid. Why? Because you can see this is the repetitive um, cell that is shared in whole particle we have. But about the non-crystalline or amorphous solids, look at this. There is no repetitive shape in whole material, but you can see find some close shapes here too, but not like the crystalline solids. But you can find, for example, these three atoms are the short range order of this material. Look at this. These are repetitive everywhere. This is what we call a short range solid or amorphous solid. Oh, look at this. This is an amorphous solid. There is no exact order for this material. Or this is not a picture for this level. Or this is a crystalline solid. Look at this. They are in a nice order that you can see. They are so clear for us. So when we talk about uh, protons, neutrons, and electrons. But what are protons, neutrons, and electrons? Um, Better to say, what is a quark? We have six quark and six antiquarks. That we have six quarks and six antiquarks. So in all, we have 12 quarks. Okay, and what are these six quarks and six antiquarks? We have up, down, strain, charm, top, bottom. These are the six quarks. And what are the antiquarks? Anti-up, anti-down, anti-strange, anti-charm, and anti-top, and anti-bottom. But what are the protons, neutrons, and electrons? Electrons are not in this uh, group, so we're not gonna talk about these electrons here. So let me talk about protons and neutrons here. You know, protons and neutrons are not elementary or fundamental particles. Why? Because let me explain what is a fundamental particle. Particle. Um, what is that? Consider an atom. We can break it to protons, neutrons, and electrons. And we can also break the protons and neutrons into up and down quarks. But until now, we cannot break the up and down quarks to to smaller particles. So they are elementary particles. They are fundamental particles. They have no smaller particles to form these particles. So we call these kind of particles as fundamental particles. So protons and neutrons are not uh, elementary particles. So what are them? They made up of two of these six quarks, up and down. Also neutron is up and down quark. So what's the difference if they are the up and down both are made up of up and down quarks? So what's the difference? The difference is that the proton has two up quarks and one down quark, and neutron has one up quark and two down quarks. Up quarks has uh, one third positive charge, and down quarks has minus one third negative charge. Actually, better to say they have one third negative charge, and this is the protons and neutrons that they made up of and down quarks. But what about these quarks? They are so heavy and they are so unstable, and they like to be the up and down quarks, so they decay and they will change in shape to the up and down quarks, and these are so stable, and we can say they are the uh, they are the cornerstone of the world, and these up and down quarks, so they are so important and so stable for the world, and they make protons and neutrons. And what about the electron? Electron is in this group. Electron is a lepton. Itself is a fundamental particle. But do leptons have hands in strong interaction? No, they have no hands in strong interaction, but instead they are have hands in Pauli exclusion principle, and you cannot find two electrons in the similar state at the same moment. For example, they cannot have same spin at the moment. Okay, and what is the spin? For example, consider this circle. Here is O and B. After after it after it rotates, here gonna be B and here gonna be A. This is 1/2 or half spin. And what does it mean? The material needs to rotate 2 times to have the first state it has. It had. But if we had a spin, one spin as a spin, with one rotate, it'll be A and it'll be B again. So this is the spin. The spin is talking about the rotation of the uh, material that we are talking about, the particle we are talking about. If we have this kind of uh, uh, actually parallel and spins for the electrons, we're gonna have a charge distribution of the electrons gonna be like this, and here is the place that they have is that these two electrons are overlap, and if this overlap is get bigger, this is gonna be unstable for our materials. So one of them is um, consider this as left hand spin, and consider this as right hand spin, and this one as left hand spin. So our electrons should have one of them should be left hand spin, and one of them should be right hand spin to be stable. And we have also 6 leptons and 6 antileptons that we call the electron as look at this, the electron is lepton and its antiparticle is positron, that we show that with E plus. This is muon and this is tau, that these three have one negative charge, but these are neutral, and they are electron neutrino, muon neutrino, and tau neutrino, and their antiparticle is with this is their symbol. And this is the uh, beta, I'm sorry, the lepton uh, leptons. And what about the weak interaction and strong interaction? A strong interaction is, I'm sorry, uh, a strong interaction is the interaction between protons and neutrons that are made the nuclei, and the strong interaction is happen in the nuclei of the atom. But what about the weak interaction? I'm sorry, uh, lepton, and here is the weak interaction. Weak interaction, before being the weak interaction, is a beta decay, and the upness or the topness or downness or bottomness quarks that in if I bring the here, this is the upness, this is upness, this is upness, and this is downness, and this is downness. For example, if this is up, this is down as a symbol. These are decaying into each other, and we call this weak interaction that is happening between quarks and leptons, and it's 10 to the power of 6 times smaller than the weak interaction. So it's a strong interaction. So weak interaction is so smaller than the uh, strong interaction. For example, neutron will decay to a proton, electron, and anti electron neutrino, or also a muon will decay to a muon neutrino, electron, and muon anti-electron or anti-electron neutrino. I'm sorry, anti electron neutrino. Yes, and um, let's talk about the fermions. What are fermions? If our material has a half spin, 1/2 spin, and that I describe that what is in a spin is, it's going to be a fermion. And if we gonna bring a classic definition for a spin, the most similar thing is the angular momentum of a material. And spins for fermions is 1/2, and if a material has odd particles fundamental particles is also uh, a fermion. For example, consider these proton, neutron, and electron. A material that has no, this should be 1 and this is 2. This material is a fermion, and fermions are hadrons, and hadrons are the gonna have 2 or 3 quarks. Okay, and these by these we can say we have 2 types of hadrons. That hadrons are the fermions, one type of the fermions. That hadrons has 2 shapes, so barium and meson. What is a barium? For example, proton is a barium. Why? Because it's made of 3 quarks. Okay, and an antibarium is uh, made up of 3 antiquarks. If we have 3 antiquarks, for example, 2 anti-up and 2 anti-down, we're gonna have a antibarium. But baryons are made up of 3 quarks, and mesons are made up of 2 quarks. One quark and one antiquark. As an example, for example, um, up anti down, for example, is a meson. And this is about the mesons. And what about the is the boson? Oh, this is the bosons. If we can have some explanations about the bosons, we're gonna have gluon, Z and W bosons, photon, and Higgs. That gluons is the force carrier of the strong interaction, and uh, for example, mm, up, down, up. The interaction that happen between these and these 3 quarks is the gluons. For example, you consider this as up and this one as down. The interaction, for example, it shows a gluon, and when it comes to here, it changed to down, and this is going to be, for example, UUD. Okay, they are the strong interaction carrier. And another thing is the W and the bosons that they have hands in weak interaction. They are the weak interaction carriers, so they are have hands in beta decay. I'm sorry for my bad handwriting with this mouse. It's so hard. It has hands in beta interaction, and um just this I'm sorry, beta decay. This is not the interaction, this is decay. Beta decay. And photon is the electromagnetic carrier. For example, consider this as symbol of photon. They are the carrier of electromagnetic uh, matrix. For example, visible light or UV or IR or some levels of electromagnetic forces. Consider visible UV/IR as electromagnetic forces, or whether these are the part of the electromagnetic period. And uh, what about the Higgs boson? If we consider the every quarks that we have, the Higgs boson is the heaviest material that you can imagine among these fundamental particles. Okay, uh, we call these as gauge bosons. These part, they are the gauge bosons. Um, Higgs boson is that much heavy that it has a field that we call that the Higgs field. That the other materials, for example, electrons, by the interaction that have with this Higgs boson, they're gonna have mass, and the Higgs boson is give them their mass. For example, um, photons has no interaction with Higgs boson, so they have this c speed or the light speed. Okay, Higgs boson will give them the uh, uh, their mass. So photons, because of having no mass, they can uh, move with light speed. This was the things that I wanted to explain. So let's review what I told you. Uh, we are going to talk about crystallography, the introduction we have. This is the first part. In the next video, I'm gonna talk about the bonds between atoms. Uh, I told you the crystallography is the field that we are studying the crystals, and the importance of that was when we know the crystal structure of a material, we can find some properties of materials, for example, its mechanical properties. Or we have solid types. Two solid types we have at least crystals and amorphous. That amorphous itself has two shapes, no order or no orientation, short range order. A crystal is made up of a regular pattern that is uh, repeated in whole structure, and it shouldn't have any gap between these two cells that between cells that it has, and they have a long range order to obey. But amorphous has no order and no shapes. And I told you that atoms are made up of their nuclei, that nuclei is made up of neutrons and protons, and its electrons that are orbiting around the material and the atom around the nuclei we have. Look at this picture. Let's take a look at it. Uh, Look at this. The clouds are here. Uh, these places are more transparent. and this is talking about the probability of the appearing the electron. You can see electrons can be here, 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 or anywhere in this cloud of electron. Okay, not just only on these circles. You can see they can be anywhere in this cloud. But why we draw them on these circles? We are talking about the let me change the color. Probability. You can see by getting near by these places, these circles, we have a very solid color, but here is transparent. Here are the places that electrons like to be there. There has more probability to be there. They like to spend their time in these specific circles more than other places. It doesn't mean that they cannot be here, here, or here, or anywhere else. Just we are talking about the probability, not exact place of an electron. So, uh, for example, here, let me change the color. Here is, and here, if you consider this 1 and 2, electrons like to be in two position. Uh, it likes to be in the two position more than the one position because these places are having more probability of appearing the electrons. And why you can study the chemistry uh, to have to gain more informations, and just this, and I told you what an atom is, that protons are made up of two protons are made up of two up quarks and one down quark, and neutron is made up of one down and one up quark and two down quarks, and we have six quarks and six anti-quarks, and the up quarks and down quarks are the most stable quarks, and these are so unstable and they like to decay to these stable particles. And about the leptons, we have six leptons and six antileptons, and in all we have 12 antileptons, but they are also the fundamental particles. These are showing the anti leptons, and we can show anti-muon, for example, with this, and with this. They are neutral and they have one negative charge, and they follow Pauli exclusion principle instead of following and instead they cannot have any hands in strong interaction, and strong interaction is the interaction happens between protons and neutrons, or better to say nuclei or nucleons. And another thing is about the fermions. What is a fermion? As I told you, a particle like this and here is B, and here is B, and this is A place. If the material rotate, it needs, if the spin is 1 by 2, it needs to 2 times rotation to have here as A again, or here as B again. So this is the spin. This is the spin, and in classic word we can say spin, and in classic word we can say spin is similar to angular momentum, and hadron is one type of the fermions, and fermions also are the fundamental particles, uh, and hadrons actually not fundamental particles, I'm sorry. And fermions are made up of quarks, and also let me as a hint on note, let me tell you that if a material has odd particles, for example 2 protons, 2 neutrons, 2 electrons and 1 neutron, it's a fermion. What if we have 2 neutrons? uh, 2 plus 2 plus 2 equal to 6. It's gonna have bosonic uh, properties, and bosons are the force carriers of the nature. Okay, so let's back to this. Hadrons are made up of 2 quarks or 3 quarks, and the particles that are made up of 3 quarks are baryons. For example, proton is a baryon, 2 up quark and 1 down quark, 3 in all 3 quarks, so it's a baryon, and baryon is a hadron. And a neutron is also a baryon. And mesons are made up of quarks and antiquarks, and an antibaryon is a particle that is made up of 3 quarks, 3 antiquarks. And if a particle that made up of baryons are baryonic molecule. For example, the atom nuclei is a baryonic molecule. And bosons. We have 4 gauge bosons: gluon that have hands in strong interaction, Z and W that have hands in weak interaction, and photons that are the electromagnetic carriers, and Higgs boson that make the Higgs field and give other fundamental particles their mass. And if they don't have any interaction with this Higgs boson, they have no mass and they can have the light speed. And another thing is about the weak interaction, that we can say weak interaction before being the weak interaction is a beta decay, and uh, W and Z bosons are the particles that have fundamental particles that have hands in beta decays, and also there are X and Y too that you can uh, have self study about that. Weak interaction is the interaction between upness and downness quarks, or quarks between quarks and leptons, and they decay to each other. And weak interaction, I show interaction with I, is 10 times smaller than the strong interactions, so it's so weak and small, and we can bring neutron decay and muon decay as the examples of the weak interaction, that neutron will decay to a proton and electron and anti-electron neutrino, and muon is going to decay to a muon neutrino, electron, and anti-electron neutrino. And just this, and if there is some problem still for you, and I gonna be responsible for that. If you have Instagram, you can follow me with this ID Golden Phonics, and also Instagram. Golden Phonics is my ID. You can contact with me, and I will be responsible for your questions, and uh, I'll be happy to help you if you want. If you have any questions, I'm available. Thank you for watching, and just this.